Imagine a world that once had rivers, a thick atmosphere, and maybe even the right conditions for life. Then, something went wrong. The rivers dried up, the atmosphere vanished into space, and the planet froze into a silent, red desert. That planet is Mars. Today, we're re-digging into one of the biggest mysteries behind its dramatic transformation. Why did Mars' core go cold? And how did that kill its ancient magnetic field? Welcome back to EverCurious, your home for stories where science meets mystery. So grab your curiosity and maybe a jacket because Mars is colder than you think.
EverCurious, learn what you love.
Mars is small, rugged, and cold on the surface, but deep inside, the story is even stranger. Unlike Earth, which has a hard, swirling liquid outer core that generates a powerful magnetic field, Mars' core is mostly solidified. Its magnetic field died billions of years ago. But here's the weird part: Mars shouldn't have cooled down that fast. Planets its size usually stay geologically active for much longer. So, scientists are asking, what accelerated Mars' cooling? Why did its magnetic heart go silent so early? To answer this, we first need to understand the magnetic field Mars used to have, and how we even know it existed in the first place. Even though Mars has no global magnetic field today, its crust holds the fingerprints of one. NASA's Mars Global Surveyor spacecraft discovered striped magnetic patterns frozen into ancient rocks, especially in the southern hemisphere. These stripes are very similar to those found on Earth along mid-ocean ridges, and they're a clear sign of a once active dynamo. This means that around 4.3 to 4.1 billion years ago, Mars had a magnetic field strong enough to shield its surface from dangerous solar radiation. It once looked like a planet with real potential for life. Something must have stopped that dynamo, and to uncover what happened, we need to journey deep thousands of kilometers beneath the Martian crust. So, what is a planetary dynamo? A planet's magnetic field comes from a dynamo, an engine powered by a moving, molten, metallic core. On Earth, this is our swirling iron-nickel outer core, which is constantly churning as heat escapes from the core into the mantle. For a dynamo to work, you need three things: a liquid metal core, convection, which is hot material rising and cool material sinking, and planetary rotation to twist those motions. If any one of these things stops, the magnetic field dies. On Mars, something disrupted these processes. The question is, was it a problem with the core itself, the mantle, or was it something catastrophic from the outside? One of the simplest reasons Mars cooled so quickly is its size. Mars is only about half the diameter of Earth and just 1/10 of the mass. Smaller planets lose their internal heat much faster. It's like a small cup of coffee cooling down much quicker than a large part. This means Mars' core was probably always destined to solidify billions of years before Earth's ever will. But that isn't the whole story. Even for a small planet, Mars' dynamo should have lasted longer than it did. Something pushed the cooling process into overdrive. One leading theory suggests that Mars suffered massive impacts early in its history. The evidence for this is written all over its surface. There's the enormous Hellas Basin, a gigantic crater, and the even larger Borealis Basin, which covers almost half the entire planet. These impacts were so powerful they could have disrupted convection in the mantle, blown apart the insulating crust, and caused a rapid loss of heat. Some models, published in journals like Nature Geoscience, suggest that a single giant impact could have been enough to freeze the dynamo within just a few million years. It would have been a catastrophic event that fundamentally changed the planet's future. But there's another compelling theory that points to the chemistry of the core itself. Studies, including amazing data from NASA's InSight mission, suggest that Mars' core has an unusual chemical makeup. It seems to be rich in lighter elements like sulfur, oxygen, and hydrogen. These elements can form stable layers within the core, preventing proper convection from happening. Imagine trying to mix oil and water in a jar. They just sit there in layers, not moving. If Mars' core formed with these stable layers, the dynamo could have choked off very early on, even if the core was still hard. This idea, known as chemical stratification, is one of the most exciting new theories in planetary science today. This is where NASA's InSight lander became a game changer. By listening for moss quakes, InSight allowed scientists to map the planet's interior for the first time, and what they found was surprising. Mars has a larger than expected liquid core, but it's much less dense than Earth's. This discovery supports the idea that the core has a high concentration of sulfur and other light elements. InSight's data is reshaping everything we thought we knew about Martian geology, suggesting that the core's unique composition might be the primary reason it cooled so quickly. The consequences of this were catastrophic. Without a magnetic field, Mars became completely exposed to the sun's harsh solar wind. NASA's MAVEN spacecraft has actually recorded this atmospheric escape happening, even today. When the magnetic field collapsed, the solar wind began to strip away the Martian atmosphere. Water on the surface either evaporated and escaped into space or froze into the polar ice caps and underground ice we see today. Surface temperatures plummeted, and deadly radiation levels skyrocketed. Mars didn't just cool down, it suffocated. The death of its magnetic field was the death of its potential as a habitable world. So, what does this mean for the search for life on Mars? If Mars only had a protective magnetic field for its first few 100 million years, then life, if it ever emerged, had a very short window to survive on the surface. This also means that any potential Martian life may have had to retreat underground to escape the radiation. The ancient river valleys we see were likely formed before the atmosphere was lost. This directs our search. Future missions must look deeper beneath the crust for any signs of past or present life. The cold core of Mars may be the very reason life never took hold there like it did on Earth. Understanding Mars also helps us understand planets far beyond our solar system. When astronomers look at rocky planets orbiting other stars, one of the key questions is whether they have active dynamos. A magnetic field can determine a planet's atmospheric stability, its surface habitability, and its radiation exposure, basically, whether life as we know it could exist there at all. Mars serves as a cosmic warning that size, composition, and even catastrophic impacts can doom a planet's chances for life very early in its history. Mars is a cold world today, but beneath its frozen silence lies a dramatic story of heat, magnetism, and catastrophe. Its core stopped moving, its protective shield disappeared. And with that, Mars transformed from a young, promising world into the barren, red planet we see now. If you want more deep dives into the biggest mysteries of the cosmos, don't forget to like, subscribe, and stay ever curious. Thanks for watching.